In the first part of this series, we explored the basic elements of a glider. In part 2, this video focuses on how a glider is controlled in the air. What can we actually control in a glider? The direction? Sure, but not like in a car. It's all about juggling bank angle, yaw and pitch in the correct way. What about height? Well, we can't just decide to fly up. We can pitch up or down and see what happens. When we use the elevator, it always comes with a change in speed. But be careful, our glider can only fly within a certain speed range. Here's the deal. We rotate around 3 axes: yaw, pitch, and roll. That's all we've got, and it has to be enough. In aviation, these axes are tied to the airplane's structure. All 3 axes intersect at the aircraft's center of gravity. The vertical axis, yaw, runs from top to bottom. The lateral axis, pitch, spans wingtip to wingtip. And the longitudinal axis, roll, runs nose to tail. To control our glider around these axes, we have the right tools for the job. The elevator for pitch, the ailerons for roll, and the rudder for yaw. Each control surface, rudder, aileron, or elevator, works much like a wing. But unlike a fixed wing, they are adjustable. Instead of generating lift, they create directional aerodynamic forces proportional to the pilot-introduced deflection. The airflow changes, creating a pressure difference that moves the aircraft in the opposite direction. This results in yaw, roll, or pitch, altering its flight path. Precise rudder control is especially crucial in our glider, where efficiency and balance define every maneuver. Let's take a closer look at how it all works. The control stick is connected to the elevator through a system of rods and various bell cranks. This simple example is just meant to illustrate the hidden mechanics. In reality, we can see many varying implementations. When we pull the stick back, the control surface moves upward, creating aerodynamic drag. As a result, the tail of the aircraft moves downward, causing the plane to rotate around the lateral axis and raise the nose. Pushing the control stick forward has the opposite effect, lowering the nose into a nose-down position. Each of these flight attitudes corresponds to a specific horizon picture. Here, we enter the nose-down position. And this is how it looks like entering the nose-up position. There is a direct relationship between attitude and airspeed. Raising the nose slows us down. However, be careful not to get too slow, or we risk entering the stall region. Conversely, the more we lower the nose, the faster we go, and we also descend more rapidly. With experience, we can also hear the difference in airspeed through varying intensities of wind noise. Alright, let's check out how these magical flappy bits called ailerons make our glider roll. The ailerons on each wing are coupled. One goes up, the other goes down. That is accomplished by a clever system of rotation angles and rods. When you push the stick to the left, the glider obediently rolls left. It'll keep rolling until you say, "Whoa there," and center the stick. Once it's in that nice tilted position, it'll stay there like it's lounging in a hammock. Since it's banked, the glider naturally starts turning. Push the stick right, and you guessed it, right we go. The more you push, the faster the turn. So handle with care, unless you want a roller coaster ride. Do you want to see how it looks from the cockpit view? Here it is. Stick to the right, the glider starts rolling, and the horizon shifts. Center the stick, and the glider will maintain the bank angle. To roll left, push the stick to the left. Students start with bank angles up to 30 degrees. With more experience, you'll be able to control angles of up to 60 degrees when catching a narrow thermal. As a beginner, it's a bit of a challenge to keep the wings level when flying through an unstable air mass. Because the wings are removable, the aileron connections must be linked. In modern gliders, this happens automatically through various solutions. The rudder controls the yaw of our glider and is operated using the pedals, which move forward and backward in opposite directions. The pedals are often connected to the rudder using steel cables. This is a simple example to illustrate the basic principle. For example, pushing the right pedal forward causes the glider to yaw to the right, but the aircraft continues traveling in the same direction. Flying this way introduces significant drag, making it highly inefficient. Likewise, pushing the left pedal causes the glider to yaw to the left. Yawing is easily noticeable from the cockpit, as the nose of the glider points in a different direction than its actual flight path. More importantly, the yaw string will shift, indicating that the glider is not flying in the direction it is facing. In the next chapter, we will deal with adverse yaw from rolling and how to compensate for this. Did I mention that life isn't that simple? We observe two effects. First, adverse yaw. When rolling, this secondary effect causes our aircraft to yaw to the left. It may appear as though the nose is rising, but this is actually due to adverse yaw. Since our glider is now banked, the rudder operates in this new orientation. Let's examine how this affects our attitude. The glider yaws around its local axis, and the yaw string correctly indicates the direction we are flying. To compensate, we simply use the rudder to center the yaw string. Once it is centered, our aircraft is precisely pointing and flying in the same direction. However, we notice another effect. The nose begins to drop. Why? Because in a banked position, the wings generate less lift. By slightly pulling back on the stick, we can counteract this. When we complete the turn and level the wings, we must release the stick. Otherwise, we will end up in a nose-up position. Okay, let's summarize this. Rolling a glider has a secondary unwanted effect. it yaws in the opposite direction. To compensate, we have to use the rudder in the same direction as the roll. Only by applying a coordinated input of aileron and rudder in the same direction can we ensure a smooth and balanced turn without unnecessary yaw. This is quite a challenging task and can be mastered more effectively with lots of practice. The better we coordinate, the more efficiently we slice through the air. In the next part of this series, we will cover the instruments, how they work, and what they are for. Stay tuned for more information on this YouTube channel.